All right, folks, welcome back to the Network TMLE session on day 2. We're really pleased today to have Paul Zivich with us. Paul is a recent graduate from UNC, now postdoc. I forget exactly which project you're postdocing for, but I know that it's continuing on the networks and health kind of broadly construed world. So as part of, I came to know Paul through his work on his dissertation and some earlier work that he did through social networks and health. And he introduced me to this notion of network TMLE, and I just thought it was a new way of thinking about some of the estimation problems we're all interested in. And so it would be a nice opportunity for him to share that with you. So Paul, the floor is yours.
Thanks, Jim. Yeah, actually, I think way back at the Social Networks and Health 2016, I think is when I met you. So, but yeah, so this work has been related to that. I'll share my screen to hopefully make it a little bit easier. So I was just going to take the first 5-10 minutes before questions, just kind of highlight some of what I think are the main messages. So one of the things in this case of network targeted maximum likelihood estimation, or TMLE, is we are interested in something a little bit different than a lot of the other talks kind of presented today. Really what we want to know is the effect of an intervention on some kind of exposure, treatment, or intervention on some kind of outcome among a group of people. And the network is important, but it's going to take a little bit of a backseat. It's important for getting our measure and the estimation procedure, but it's not the thing we're trying to draw inference about itself. So an example of kind of the questions we can ask in this case is, maybe we want to know, if we were all meeting in person, what if everyone had like a 60% chance of receiving the COVID vaccine, what would be the expected number of COVID cases after the workshop, right? So we could ask those kind of types of questions. It doesn't have to be infectious disease, but anything we can think about as transmissible or contagious. And all of those things are driven by the network, but we're not trying to learn about the network itself. So the thing we're trying to talk about, all the framing I use is developed from the causal inference literature, particularly the causal inference with potential outcomes. So if you are interested in a lot of this work on like a deeper level, most of the causal inference literature with potential outcomes is thought about independent observations, right? And you can kind of think of that as just like a special case of networks where there's no edges, right? All the nodes are independent, no connections. So having a little bit of an understanding of that helps a lot for some of these more complicated methods like network TMLE, right? There's a TMLE for independent data. This version just builds on another layer and has some additional complexity that it needs to account for. So a lot of my understanding was furthered by thinking about these independent data cases and then kind of expanding to that. So in the independent case, this is kind of what we're estimating. So what it is we have some treatment plan or way we're going to assign our treatment, which is A. So, you know, if it's a vaccine, I'm going to set everyone's probabilities, right? Like the special case is I give everyone a probability of 1, so everyone receives the vaccine. But you can also think about it more generally, where we have probabilities conditional on some variates and we're assigning them. And we want to look at the potential outcomes under those assigned values, and we're doing it for the expected value of population. So this is the independent case. Network TMLE expands everything a little bit to this more complicated looking thing, because we need to start thinking about the network. And now our policies both are determined by the individual's exposure and their immediate contacts, right? So now we're allowing for what in the causal inference literature is referred to as interference, right? So other units can affect my outcome now in kind of looking at this. So what the inference kind of is for this crazy equation, or crazy looking equation, is we can suppose that we have a bunch of copies of our network, right? So we have this network, we have a very large number of them. And what we want to do is we want to know the mean of the outcome in those networks all under the same plan, right? So something like giving everyone a probability of 0.6 to get the treatment. So we can imagine this collection of networks that are all these different applications of our policy because there's some kind of randomness and there's some overall mean for them. And what we're going to do is we have our single network that we got to observe, and we're going to draw inference for that mean of across all those kind of networks. So it's a little bit different if you're used to like asymptotic results. Normally, now instead of a bunch of n independent units, we have one dependent network of a bunch of observations. And we're going to draw inference for that. So psi in this case would be something like, what is the mean of, what's the proportion of COVID infections had everyone been vaccinated at this set level? And network TMLE, it is the estimation procedure that we're kind of using. And essentially what it does, it's going to take we're going to model two different processes. One is how individuals in our observational data got the treatment, right? So maybe it depends on age. And then we're going to model another process. We're going to model the outcome process, right? It's how people get infected. So it could be age and your immediate contacts, age, or different kind of behaviors. How much do you wash your hand? So we're going to model those two processes. And we're going to combine them in a clever way. And the nice thing about how we're combining them in a clever way is we get this extra piece called double robustness. So basically, we only have to get one of those two models right. So essentially, we kind of get two throws of a dart at a dartboard to get our model right. And as long as we get one of those right, we're going to be set. So this is what I think is a useful piece of this method. As you may have noticed from the recording, there's a lot of stuff that happens in the background. We have to do a few different Monte Carlo procedures to approximate stuff. So I wrote a software package as part of my dissertation that does all this. Should also mention there is a version in R called TMLE net. However, there are a couple caveats. So there's like, in a book chapter in this book, they provide the code. However, all of the syntax is no longer like valid for their code library, and also no one has touched the library in 5 years. And there's some documentation that's not exactly clear. So while it does exist in R, you do have to do a lot more work. So my hope is I've at least tried to make my documentation a little bit easier. Plus, you can always email me, I guess. So that's the high level overview that I want to provide. So I'll take any questions.
Thank you very much. Appreciate it. Just to maybe again kick us off here a little bit quite quickly, do you have a sense of the situations under which this model is going to work well versus when it's going to work poorly, and sort of like when you're going to need it and when you're not, that kind of thing?
Yeah, when are you going to need it or not? That's a good first question. So when you would need it essentially is anytime we're trying to learn about a causal effect of some treatment we want, and we're worried that my treatment affects your outcome. Now, there's some things we might not worry, right? Like statins for cardiovascular disease. We're pretty confident that whether I take a statin is probably not going to affect whether Jim gets cardiovascular disease, right? But that's not true for a lot of infectious diseases, or if we're concerned about behavior outcomes. So anytime we're thinking about things that are transmissible or contagious, and we have some reason to believe that that happens, we're going to want to opt for these kind of methods. One of the things is this method requires a lot of network data. So it assumes you measured your network well and correctly, and all the edges are the transmissible edges. There's another general approach in the causal inference literature called partial interference. It tries to ignore the network, and what it relies on is that you can kind of divide the people in your data set into independent groups where they can all kind of affect each other, but they can't affect people across groups. So like maybe a lot of the examples in literature are like remote villages, right, that are more disconnected from each other. So it's a little bit more, makes sense for partial interference. So this method does have some practical constraints. So like people often want to know sample size things. So depending on how many covariates you have to adjust for, the method's going to be pretty sensitive to that. So like if we have one binary covariate, you can probably get away with a network of like 100 to 200 observations. But as we get more and more covariates, which is more likely to be true kind of if we're doing causal inference with observational data, you're gonna want more and more. It's gonna be hard to go below 400-ish. The other thing is it also kind of depends how common your exposure and outcome they are. The more common they are, the less observations you kind of need in general. There's also some network structure components. As you get more and more power law degree networks, those are a little bit harder to learn about. So there's this assumption that's mentioned in the slides called positivity. It's not thinking happily about your data, but what it essentially stipulates is that everyone has an opportunity for your treatment or your exposure. In networks, this kind of generalizes to also your contacts. And the problem is you can imagine a network where one person's connected to everyone and they were treated. It's hard to say what they would have looked like or what they would look like or what the outcomes would have looked like in the network if they were untreated, because you don't have like a stand-in for them in your data set. So that's another kind of limitation. Usually the approach is you draw a box around that person and you kind of leave their treatment as is and think about changing the treatment in the rest of the network.
Okay. Interesting. Is it your intuition then that that this model sort of requires that kind of middle ground of somewhere between 30% and 60% treated, as opposed to like an 80% adoption rate or something like that?
So it kind of depends what you want to learn. So as I mentioned, there's those different policies we can kind of think about. So in the most extreme case, you can think about everyone having a very low probability of getting the treatment, right? Like let's say 1 to 5-ish%. And I could want to learn about a policy where nearly everyone gets the treatment, right? So their probability is like, let's just say 1 for simplicity. Making that jump between those two is going to be very difficult unless you have a very large data set. And the reason why is if the treatment is that rare in the population, it's unlikely you're going to see any individual have all of their contacts with treatment, right? Just because it's rare. So you don't have the support in your data to kind of infer about those policies. You can look at more local changes though, right? So you could look at like, what if I shifted it to 10%, right? A smaller data set is probably going to be able to support those kind of shifts that you could look at for your policies. So it kind of depends what exactly you want to learn, and there's just going to be constraints on your data. So you might just be able to learn things closer to how the world currently looks, which may or may not be supported depending on what you want to learn.
Other questions or comments? I mean, I can dominate the discussion, but that's never fun.
Could I just ask a quick clarification question? So a moment ago, you were talking about the number of covariates in the model being sensitive to that. I didn't quite catch, I've been taking notes. You said As you get more covariates, it's hard to go below about 400 observations, but it depends on how common the exposure is and the outcome. And then I wasn't sure if you were saying if it's more common, you needed fewer observations. Was that what you had said?
Yeah, so if you have, I should say, better balance between the two.
Okay.
So if you have like half and half treated and untreated, and half have the outcome, you're going to need less observations because there's just more support in the data. But if like 1% have the outcome and 99% don't, you just don't have a lot of information to estimate that outcome process model, right? So it generally just kind of requires more observations. This generally holds true in the independent setting as well. It's just the network is a little bit harder because now we're thinking and modeling not just your covariates, right, your individual covariates, but also the covariates of your immediate contacts. So it's kind of just expanding like the dimensionality of our problem we have.
Please, Ken.
Okay, I'm going to out myself as being not sort of versed in the statistical literature in the way that I should be. But hopefully this is it's a question that's helpful for me, but hopefully it's helpful for others too, is today we've heard a lot about various simulation approaches. I mean, in particular, the stochastic actor modeling approaches. And while I think I understand sort of the big lines of that kind of approach, and I understand the big lines of what you described, I don't think I'm as clear as to how they diverge fundamentally. Why couldn't I just approach a version of my network without an intervention and a version of my network and imagine, so I have an observed network with an intervention, and why can't I simulate versions of that intervention from an actor standpoint and use the strategies we heard earlier? There's probably an obvious answer here, but I just need a clarification.
Yeah, I think so. The stochastic actor-oriented model uses a little bit different data here. At least for the example I talk about, we just need a network and covariates kind of measured at one time point and outcomes measured later, right? We don't need the repetition, but the repetition has other things that we can later assumptions, but that's one piece. The other piece is one of the other contrasts is kind of the approach of what we're doing or how we're getting to our end product. TMLE generally kind of is just is built on regular statistical models, right? So when I talk about estimating the outcome process or the treatment process, we're just using something like the logistic model or a linear regression. It's pretty generic in that sense. You can also start thinking about using machine learning in this aspect. There's a couple of caveats to that. TMLE has like some restrictions on what machine learning you can kind of use. But the point is that's kind of all left up in the air. You can choose whatever your favorite algorithm is. This is kind of just a process that tells you how to put all these pieces and predictions kind of together. So it's less of trying to estimate some of all of these coefficients. And the other key difference is we're only looking at one exposure or treatment, right? We're kind of really narrowing our focus on one thing and doing the best we can to estimate that one thing. My impression, at least, is a lot of the stochastic oriented models want to model how the network is kind of being built and all of different variables and kind of their interrelationships, which can sometimes be more difficult depending on how things are kind of set up. So we're just kind of abstracting away a lot of the extra kind of pieces. So that's like the philosophy of a lot of the TMLE and modern causal inference methods.
Okay, thank you. That's really helpful, actually.
One of the things for those of you that don't know the project, a lot of this was developed in the context of the X-flu study. So it was also a COVID-like disease. That made me wonder recently if we couldn't use this to evaluate the effectiveness of a lot of the different campus choices that have been made for trying to stop spread of disease where we have good data, right? So we could well look at, compare one campus to another. We know the courses the students took. We know the dorms they live in. We know the implementation and testing regimes. So you could think of something like locking down a dorm as a treatment. This might be a good option to, I'm just curious if you think this would be a good option for evaluating those kind of things.
I think it has potential to. One of the disadvantages, at least on that scale, is you need a lot of richly detailed network data that we may not have, right? So
that's the thing. We have co-presence in the dorm. We have co-presence in the classrooms. Right? We don't have like a lot of the interpersonal directive. We have pretty good proxies for it through those things.
Right. So you could use the proxies to kind of construct the network, but I think what could potentially be more useful in that case, just because we have those proxies already, is some of the partial interference methods. There's various work on trying to relax that and allow the units, or not the units, but the clusters to interact with each other. So it seems like just on the scale of that data, those approaches might be a little bit more tailored to this kind of problem setup.
Perfect. Awesome. Any other questions for Paul at the moment? All right. In his lecture notes and slides, there are links to the current Python package. I know that most of this has been in R, but if this is a technique you want to use, maybe you can help him translate it into R for the rest of it. Awesome. Thanks, Paul.